So, hi everybody. Okay.
Lecture23.
Okay. So last. Okay. So. And this is the last lecture on linear algebra. In fact, we're going to start differential equations in this lecture. And that's going to be heavily related to linear algebra, but it's the last lecture that's explicitly about linear algebra. And so we're going to do three things in this lecture. So, okay, it looks like I need to get the glove. Sorry. Okay. So the first thing is I'm going to finish talking about the singular value decomposition. So that's section 7.4. Then I'm going to tell you a cool application of the SVD. So the SVD is maybe the most useful thing in this course for for applied math or computer science kind of applications. So I'll give you an image compression application. And then finally, we'll move on to differential equations, where I will talk about second order ODE, which is an important class for physics, where ODE means ordinary differential equations. So, okay, so what did we do last time? So last time, I told you what singular vectors were, right? And okay, there was a sort of elaborate procedure for finding these vectors, right? So if you have an m by n matrix A, then you form this n by n matrix A transpose A. And then because that's a symmetric matrix, by the spectral theorem, it has an orthonormal basis of eigenvectors, right? So A V1 equals lambda 1 V1 all the way up to A Vn equals lambda n Vn for some V1 through Vn, an orthonormal basis of Rn. And these lambdas are the eigenvalues, and we saw that they were non-negative, and so we can order them like this. And it was important to count how many were positive. So let's say the first R of them are not 0. And then let's say the rest of them are 0. Okay. And I should say, so somebody asked me this maybe after the lecture. You know, these eigenvalues, I'm not saying that these numbers are distinct, right? The same number could be repeated many times in this list, right? For example, if A transpose A is the identity, then you just get 1, 1, 1, 1, 1. So all I'm saying is that we know there are n orthonormal eigenvectors by the spectral theorem. And for each of them, there is some eigenvalue. And I'm just going to write down those numbers like this. Okay, so once you get these, once you get this orthonormal basis, this turned out to have a number of nice properties. So we proved this theorem, which was that the rank of the matrix is equal to R, which is the number of non-zero lambda I. Okay. Then we proved that if you look at the corresponding eigenvectors of A transpose A, this are an orthonormal basis of the row space. And then we proved that if you now look at, so the last step was you define these new vectors, U1 equal to A V1 divided by sigma 1 all the way up to UN equal to A, or I guess only up to UR equal to A VR by sigma R, where these sigma I are the square roots of the eigenvalues for the non-zero eigenvalues. Then you get that these are an orthonormal basis of the column space. Okay, so you have this very special pair of orthonormal bases like this. And you know, these are called the left and right singular vectors, and they're related by this equation. A VI equals sigma I UI when I is less than or equal to R, and A VI is just equal to 0 for I bigger than R. Okay, so this is really a lot. Okay, I mean, this is in some ways, I mean, this proof uses everything we learned in this course. Okay, and I didn't learn this proof until I learned it in graduate school, and even then, it took me a while to really internalize it because it has so many moving parts. So don't feel like there's something wrong if you didn't understand it during the lecture. You really have to go through this proof again on your own, and ideally explain it to somebody else, because there's so many moving parts, right? It uses row rank equals column rank, orthonormal basis, spectral theorem, you know, facts about transpose. It uses everything. So it's a good way to make sure you understand everything. And what I'll show you now is that it also is worth it because it has so many consequences. But this is a cap of what we did last time. So any questions about this before I proceed? Okay. Wait a minute, my eraser doesn't seem to be working, but okay. Okay, so these are the right singular vectors, and these are the left singular vectors. Okay, so for first, let me just compute these things for an example, just so it becomes a little less abstract. Here's an example. The example is the following matrix. So let's see, I wrote down a matrix somewhere. Right. Yeah. So I have this matrix, 1, minus 2, 2, minus 1. Wait a minute, is that really what I wanted? Yeah, okay, minus 1, 2, minus 2. Okay. So that's a matrix. And what I can do now is I can form A transpose A. So the first step in this computing the singular vectors is to form A transpose A, right? So let's do that. So A transpose A. Okay, so you know that's literally the transpose of this matrix. So 1, minus 2, 2, and then minus 1, 2, minus 2 times the matrix. So 1, minus 2, 2, minus 1, 2, minus 2. And okay, let's start doing this. So I get 9. And then on the off diagonal, I get minus 9. And then here I also get minus 9. And here I get 9. So that's a 2 by 2 matrix, right? So this is a 3 by 2 matrix. This is a 2 by 2 matrix. And now, actually, in the last lecture, I actually, you know, this is actually 9 times the symmetric matrix example from the last lecture, right? That's kind of why I chose it. I was planning to cover it in the last lecture itself, but right. And we already computed the eigenvalues and eigenvectors of this matrix, right? So step one is to form A transpose A. Step two is to find the eigenvalues and eigenvectors, which we already did. So the eigenvalues turn out to be 18 and 0. So lambda 1 is 18, lambda 2 is 0. And we found an orthonormal basis of eigenvectors in the previous lecture, which I'll just remind you what it was: 1 over square root 2 minus 1 over square root 2. And V2 is 1 over square root 2, 1 over square root 2. And these square root 2s are there because I want to normalize these to be unit vectors. Okay. And now step 3 is to compute the singular. So these are the right singular vectors. Right singular vectors. And now to compute the left singular vectors, I have to hit this with A, right? So step 3, I have A V1. If you work it out, it's this vector, 2 over square root 2, minus 4 over square root 2, 4 over square root 2. And AV2 is, well, it's just 0. Okay. And that makes sense because lambda 2 is 0. And the corresponding singular value, sigma 1, is square root lambda 1, which is 3 square root 2. Sigma 2 is just 0. Okay, so now I've computed, so now to compute the left singular vector, they have to normalize. So this is A V1 divided by sigma 1, which if I do this, so I have to divide this by 3 square root 2. I get okay, so I have to divide this by 3 square root 2. So that's going to be, let's see. Well, it's just going to be 2 over 6, and then minus 4 over 6, and then 4 over 6, otherwise known as a third minus 2/3 and 2/3. Okay, and then U2 is not, because you can't divide by 0, U2 is not defined. So in this case, the rank R, which is this important quantity, is just 1. And that makes sense, right? I mean, at this point in the course, you can just eyeball this matrix and you're like, yeah, these columns are linearly independent. The rank is 1, right? So in this case, indeed, we found the left and right singular vectors, that the rank is 1. So these are the left singular vectors. And these are related. You can check, by the equation AV1 equals sigma 1 U1. Okay. So any questions? I haven't told you what this is good for yet, but any questions about the computation?
Why do we divide the singular values?
We divide them because we want UI to be unit vectors. So remember, in the last class, we did this derivation where we saw that sigma 1 is just norm of AV1. That's generally true, right? And so then that means that U1 is a unit vector. So this is just normalizing a unit vector.
Okay, thank you.
I mean, yeah, so as I said, like all the pieces of this fit together in a really tight way. So that's the difficulty, but that's also sort of the beauty of it. Okay, any other?
Why are they called right and left singular vectors?
Well, because V1 through VR span the row space, right? And I mean, I'll tell you just in a moment. It'll be more obvious in a moment, actually, when I tell you what the singular value decomposition is.
Okay.
So hold on a second. Okay. Okay. So now, what is the singular value decomposition? So let me tell you what that is, right? So singular value decomposition is the following. So it's actually a couple of things. So I'll tell you the one I think is more interesting first. So suppose you have an m by n matrix. And now you have these equations, right? AV1 equals sigma 1 U1. AV2 equals sigma 2 U2. All the way up to AVR equals sigma R UR. And these are not zero, right? These are the positive singular values. Sorry. Okay, so what I'm going to do now is I'm going to show you something that's called the reduced singular value decomposition. And this is something you get just by writing this information in matrix notation. Okay, so let's write all these equations in matrix notation. Well, you have A times, so that's an m by n matrix, times, let's form a matrix of the right singular vectors, the ones corresponding to positive singular values, okay? This is an n by r matrix, right? Now up here, I have r equations, right? Oops, I don't know what just happened. Yeah, I have r equations, right? So I'm going to just write those as columns of a matrix equation, right? So this is equal to sigma 1 U1 all the way up to sigma R UR, right? Nothing fancy here, just wrote it in matrix notation. But now I'm going to do something a little bit interesting. I'm going to write this as a product. I'm going to write this as sigma hat. So, well, let me just write down the matrix. I'm going to write this as the diagonal matrix, which has sigmas on the diagonal, square matrix, R by R, times, okay, I guess I should move this line a little bit, the matrix of views. And this is now, oh, sorry, I wrote it backwards. Oops, yeah. I'm going to write this as the matrix of views times a little square matrix, maybe not that little, of these R's. And this makes sense, right? Because this is an M by R matrix. This is an M by R matrix, and this is an R by R matrix. So I've not done anything. I'm just rewriting the equations, right? So write equations in matrix forms. Any questions about this writing? Okay. So I'm now going to give these things names, right? So let's call this V. Let's call this U. And let's call this sigma hat. So now I have a matrix equation, namely AV equals U sigma hat, right? And now I'm going to multiply both sides on the right by V transpose, right? So A V transpose equals U sigma hat V transpose. So if I multiply by V transpose, just again, to maintain sanity, just keep track of the dimensions now. So V is a n by R matrix, right? So V transpose is R by n. And so now this whole left-hand side is n by n. What am I saying? M by n. Okay. And now the nice thing that happens is, I mean, maybe I won't write it in a separate line. The nice thing that happens is A VV transpose is just equal to A. Okay, now the proof of that is, well, there are like 10 different ways to prove it. Let me give you maybe a very conceptual chapter 6 way to prove it. So let me call this thing star. Okay. Or actually, maybe I'll just remove this column and prove star over here. Star has a very cool proof. So I want to prove that A is equal to A times VV transpose. Now, what is VV transpose? Well, it's the projection onto the row space of A, right? It's the matrix of that projection. Because remember, V is an orthonormal basis of the row space. That's what it says over here in item 2. But now, suppose I take A times a vector X, right? That's the same as A times the projection onto the row space of A of X plus the projection onto the to the null space of A times X. Why is that?
Because the null space is like the row space perp.
Yeah, the null space is the orthogonal complement of the row space. So I'm using some fact from, I guess, section 6.1 here. But now, okay, the projection onto the row space is AVV transpose. So this is AVV transpose times X, right? Plus A times the projection onto the null space of A times of X, right? But what is that second term? If I project a vector onto the null space and then apply A, what am I going to get?
I'm going to get a 0 vector because the null space is just 0, right?
Exactly. Yeah, A kills the null space. So this is 0. So indeed, AX is equal to AVV transpose X. And this is true for every X. So that is the reduced singular value decomposition. Okay, this is the end result. Is that A is equal to U sigma hat V transpose. Okay, so, what is the meaning of this? So let me write down the meaning of this. So, okay, so it's ultimately a factorization, right? I'm factoring A into a matrix with orthonormal columns times a diagonal matrix times a matrix with orthonormal rows. Okay. Right, and the dimensions of these are, this is M by R, this is R by R, and this is R by N. So when you multiply them, you get an M by N matrix as desired. And what's the interpretation? Interpretation of this is, well, so suppose you multiply this by some X, right? So then this is U sigma hat V transpose X. And if you do the usual song and dance with the projection formula and so on, you get that this is just summation over the singular values, the non-zero singular values of Vi dot X times Ui times sigma I. So what that means is you've written A as summation sigma I Ui Vi transpose. And so what this means is you've written your matrix, which has rank R, as a sum of R rank 1 matrices, each of which does something very simple. It just takes a dot product with one of the right singular vectors and outputs just that number times the corresponding left singular vector. Okay, so this is saying that a rank R matrix is a sum of R rank 1 matrices which look like UI, VI transpose with weights, singular values. Okay, so that's the interpretation of the reduced SVD. So just to hash it out, in our example, what's the reduced SVD? I mean, it's actually not anything complicated. It's just, you just rewrite the singular vectors in this format. You don't have to do anything new. So let's write the reduced SVD. Reduced SVD in this case is that A is equal to U. So in this case, U is this matrix, a third minus 2/3, 2/3. Sigma is just a 1-by-1 matrix containing the singular value 3 square root 2. And V transpose is just a 1-by-2 matrix, in this case containing V1 transpose. So this is the reduced SVD of this matrix. In this case, it's very simple. There's only one term. Right? So this is U, this is sigma, this is V transpose. Sigma hat, I guess we're calling it. So this is telling us that the way to think of what this matrix is doing is it's projecting onto this one V1 vector and then just outputting whatever that length is times this U1 vector times a singular value. Now, this interpretation will be useful in the application, but any questions about the interpretation for now? So unlike a lot of the things we did before the first midterm, this is the part of linear algebra that it's not just a language, right? It's not just we're making up a language and playing some game with that language. It's really a fact, a non-trivial, like sort of deep fact about matrices, which is not obvious at all when you just start thinking about them. So any questions about the interpretation or this proof?
Yeah, with the last part of the interpretation, like the part where you boxed in blue, where it's like A is equal to sigma, or the sum of like a sigma I, is that UI?
UI VI transpose, yeah.
Yeah, transpose. Why is it UI? Did VI dot X? Why does that become UI again?
Right. Well, because think about this term, right? What this is really summation sigma I UI VI transpose times X, right?
Mm-hmm.
But that's exactly what's written down there. If you take the X, if you remove the parentheses and move the X to the front.
Okay. Okay, yeah, that makes sense.
Yeah, it's a little confusing. So yeah, I mean, yeah. And okay, to be honest, I mean, okay, me, like when I see a matrix, I want to write it as a sum of UI VI transpose. That's what I want to do. But I didn't really start doing that till grad school. So if it doesn't come naturally to you, don't worry, just do a few problems and then, yeah, it takes a little bit of change of perspective. Wait, what? Did I just clear that page? What? Okay. At least it's in the video.
You could probably undo.
Really? Oh, okay, amazing. Thank you. Okay. Wow. I wish I'd known that earlier. Anyway, okay, fine. So good. So that's the reduced SVD. And that has this interpretation, which is sort of an additive interpretation. It allows you to write A as a sum of some other matrices. So I'll just put additive multiple interpretation here. Okay. Now in the book, they emphasize something else, which I think is less important, but I'll just briefly discuss it, called the full SVD. And the full SVD has the same starting point. So you have these equations, AV1 equals sigma 1 U1 A VR equals sigma R UR. But then you just pad this with a bunch of more equations, right? So you also have A VR plus 1 equals 0, all the way up to A VN equals 0. You can write those down. It's legitimate. And then you can also do this sort of, somewhat artificial thing, in my opinion. So you have U1 through UR, which is an orthonormal basis of the column space of A, which lives inside Rm. What you can do is, using Gram-Schmidt, you can extend this to an orthonormal basis, U1 through UR. So this is the same as you had before, but now you throw in some new vectors artificially of Rm. Okay, so the new part is this. And here again, the new part, the thing you're writing that's new is this. And if you write all this information in matrix form, you get that A times V1 up to Vn up to Vr, but now you have these new vectors, Vr plus 1 up to Vn equals this matrix of U's, U1 up through UR. So those are the sort of non-trivial equations, but now you have these new padded vectors that you added. And now times a sigma, which is sort of a weird looking matrix. It's not actually square. It has the non-zero singular values, but then it just has zeros, padded so you have the right dimensions, right? So this is m by n, this is n by n, this is m by m, and this is m by n. Okay. Now, what is the point of doing this? This looks kind of silly. How are the padded vectors added? You use a Gram-Schmidt, right? Or at this point, so let me just say these new vectors are an orthonormal basis of the column space of a perp. Okay, so right, and if you take a union of that with a basis, so this is a orthonormal basis of column space of A. Right, okay, so okay, maybe just to be fully explicit about what these vectors are. These V1 through VR are an orthonormal basis of the row space of A. And these VR plus 1 through the rest are an orthonormal basis of the null space of A. And similarly, you can find these other U's. But now the upshot of this is that, the whole reason for doing this is that this is now an orthogonal matrix. And this is also orthogonal. So let's call this V and let's call this U. And let's call this sigma. And now, if you multiply by V transpose, you literally get, that A V transpose, which is just A now because it's orthogonal, is equal to U sigma V transpose. And that is the full singular value decomposition. And the benefit of this is that U and V are now orthogonal matrices. And this is not quite diagonal, it's kind of diagonal-ish. Because it's a diagonal matrix padded with zeros. And okay, the theorem is, the sort of amazing theorem is that every matrix can be written in this form. And same with the reduced SVD, right? So let me just write a theorem. So here's, maybe if it wasn't so clear, every matrix can be written in this form. And again here, the amazing theorem is every matrix has, the above full SVD. Okay, so one way to okay, what is maybe I should say what is the interpretation of the full SVD? So the truncated SVD had some interpretation. What is the interpretation? Well, it's a multiplicative interpretation. And in this case, the interpretation is, well, what is it? What is the geometric interpretation of an orthogonal matrix? What does it do?
Does it act as a basis?
Yeah, it's an orthogonal basis. But geometrically, if you had to pick one word, like let's say in R2 or R3, what would it do to vectors?
Rotation.
Yeah, rotation, maybe flipping and rotation, right? It doesn't change the norm. Multiplicative interpretation is A is equal to, right, U sigma V transpose. And this is a rotation. This is a scaling plus maybe adding or ignoring some coordinates. That's what the padded zeros are. Plus, change M to N, basically, by either by adding zeros or cutting some coordinates. And then this is another rotation. So what this is telling you is that every matrix looks like that. And that is quite an amazing fact, right? Because we saw that matrices can represent like tons of different things. But what this is telling us is that every matrix is just a rotation, some scaling, and then another rotation. So that's the full SVD. And computationally, the only new thing you have to do is this extending a basis. So this is the new computational step. And since there's nothing subtle about this, I'll just leave you to read the book and do the exercises for this computational step anyway. But any questions about the full SVD? Oh, yeah, sorry, the handwriting is getting very bad. Let me clear this up. It says multiplicative interpretation. Okay, so you have this truncated, reduced SVD and full SVD. And they're both useful, right? It's like you had the two interpretations of the spectral theorem. You have two interpretations of the SVD, multiplicative and additive. They're both useful. So now so this looked like a huge pain. I mean, maybe not a pain, but we use like everything, right, to produce this factorization. So what is so good about this? So it turns out once you have the SVD, you can compute everything else that we talked about in this course about the matrix. Okay, so let me now tell you the benefits of having an SVD. So, so some people call the SVD is the Swiss Army knife of linear algebra. So why is that? So what do you know when you have the SVD? So, well, first of all, you have the rank. So R is equal to the rank of A, right? This is the number of non-zero singular values. Right, so let's say you have, you have the full SVD, or maybe you have the reduced SVD, right? Let's just write the reduced SVD for now. Okay, but now you also have, so V transpose is the projection onto the row space. We just saw that earlier. It's a matrix of the projection onto the row space. U transpose is the matrix of the projection onto the column space. right? So once you know this, you not only do you know the row space and the column space, you have nice bases for them and nice projections onto them. You can solve least squares if you know the SVD. So let's just check this. So how to put it? So if A has the following reduced SVD, U sigma hat V transpose, then X hat equal to V sigma hat inverse U transpose B is a least squares solution of AX equals B. Okay, so once you have this, you can just read off the least squares solution. So let me put this in a box. And okay, let me briefly explain the proof of that. Well, let's just check, right? So what is A times this thing I've stated? A times V sigma hat U transpose B. Well, what is that? That's U sigma hat V transpose V sigma hat inverse U transpose, right? B. So by the way, this is AX hat, right? And here I just use that, this is the reduced SVD. But now, anybody see some nice cancellations happening?
Everything cancels except B, so we're just left with B, right?
Not quite, almost. So this cancels. Why is V transpose V is the identity, R by R identity? Why is that?
Orthogonal.
Yeah, columns of V are orthonormal. Good. So now you get U sigma hat inverse U transpose B. That's just identity, right? R by R. So you get U transpose B. And anybody recognize what that is?
It's the identity because it's orthonormal basis.
It's not the identity.
Oh, it's a projection. Sorry.
It's a projection, yeah, exactly. Because U here is an M by R matrix, right? So this is the projection onto the column space of A, of B, but that's what a least square solution is, right? It's the solution to X equals B hat, and this is B hat. Okay, so once you have this thing, you can really do everything else with it.
Are these all for the reduced SVD?
These are all for the reduced SVD, yeah. So I personally prefer the reduced SVD, and that's why I presented it first and emphasized it more, because you can read off more things from it. Although, of course, if you know the full SVD, you can form all of these matrices as well, but these are all for reduced. Because remember, if it was a full SVD, then VV transpose would just be the identity, right? UU transpose would just be identity, so it wouldn't make sense for the full SVD. Any other question? Okay, now this list just goes on and on and on, right? Like this is like, I mean, everything you learned in the course is somehow related to the SVD, and there are homework problems forcing you to discover many of those relationships. But, in particular, you can do all of these things, which, are not so easy to do from scratch. And I should just make one more remark. So how is this related to diagonalization? So this is an important thing to understand. So, this seems great, right? You can do it to every matrix. Whereas diagonalization, you couldn't always do it. This always gives you orthonormal bases. whereas diagonalization does not. It just gives you some basis, right? So diagonalization is A equals VDV inverse for some square matrices and invertible V. Whereas SVD is A equals U sigma V transpose for U and V orthogonal for all matrices. Right, so this is for some matrices. This is for all rectangular matrices. So why is, why should we care about diagonalization? Like,
the singular value decomposition of a square matrix is the diagonalization.
Okay, that's a very good point. So comment number one is, or I mean, I guess I'm running out of space. So let me just write one here. So that's actually not true. It's true for a symmetric matrix. So if A equals A transpose, sigma just equals, so the singular value is just the absolute values of the eigenvalues. That is correct.
Professor,
Mm-hmm.
if you don't mind, but in your proof, when you subbed in x hat, shouldn't the sigma hat be inverse?
Yes, thank you. That was a mistake. Yeah, thank you. Of course, I even used that in the next step. Yes, thank you. Right. So, okay. So, I mean, I encourage you to think about this. There are many differences. And what I've written here is a relation, but really the main difference is diagonalization gives you a single basis. It gives you a single input and output basis, right? So if V is a basis, then this, the meaning of diagonalization is that the matrix of A in some basis is diagonal, right? Same input, same output basis. And this has many benefits, right? For example, then you can do things like take powers, right? Right. So these are some of the nice consequences of diagonalization. For SVD, you don't have that. Okay. The main weakness of SVD is you have two bases. You don't have one basis. Right. So the interpretation is if you write A with respect to a pair of orthonormal bases, then it's kind of diagonal. Right. But you have two bases here, and here you have one basis. Here you have two bases. So that's what you pay. Okay, so it's not a substitute for diagonalization. It's just a different thing. Okay, so this is the full SVD. Okay. Yeah. Okay. I guess this just ended up being sort of a side comment. So I don't know. I guess this slide is not very well organized, but this is four symmetric matrices. But what I encourage you to do is really incorporate this into your web of concepts, because it really is. It is related to a lot of things, and it's also different from a lot of things. Like singular values are not the same thing as eigenvalues, right? For symmetric matrices, they're closely related, but in general, singular values are not the same thing as eigenvalues, or and can have no relation to them also. Okay. Okay, so that's what I want to say about SVD. Let me now show you an application. Are there any more questions? Are there any questions about this?
Professor, do you mind explaining again how A equals A transpose gave us information about what you wrote right there?
I didn't explain it, so I'm just going to leave this as an exercise. Yeah, I leave it as an exercise.
I had a super quick question about the in general comment you just wrote. I thought that we defined the like sigma I as the square root of lambda I.
Right, but remember, sigma I is the square root of lambda I, but lambda are the eigenvalues of A transpose A, not of A.
Oh, okay.
Right? So this is the key difference. The sigma i's are fundamentally related to A transpose A, whereas lambda i's only make sense for square matrices and are related to A.
Okay.
And this kind of hints at the answer to Sandra's question, right? For symmetric matrices, A transpose A is just A. Sorry, A transpose is just A. So A transpose A is just A squared, right?
Oh, okay. Yeah. Okay, thank you.
Okay, so let me now show you a cool application of this. So the application is an application to compressing images. And this is really actually how images are compressed ultimately. So let me show you a picture. Okay, so this is a picture of a tiger. And this is a, I guess, 1600 by 1000 pixel image. And so, you know, in order to, so let's say I want to store this, this image. Let's say I want to store it in grayscale, right? So I don't want to store the colors just for simplicity. So let's say I want to store this image. How many numbers do I need to write down? So let's think about that. So you want to store I guess an 800 by 500. Let me just assume it's half the dimensions, just because the experiment that was done was for that image. So grayscale image of a tiger. Okay, so what's an image? Well, it's actually just a matrix, right? And the IJ entry is the, you know, intensity on the black and white scale of the IJ pixel. Right, so this is pixel. And so to store this, you know, how many numbers do I need? So I need, well, let's multiply this, right? I need 40 times 10 to the 4 numbers, which is, well, I don't know if you want to do bits or bytes. I mean, I think this is about 1 megabyte. I don't know. So it's several hundred kilobytes, right? If you just want to write down these numbers, that's how much space it takes. So suppose I want to store this image using fewer amount of space, right? Which we actually do want to do on the internet, right? So the idea is take this matrix and write the reduced SVD. Okay, so when you do this, you get some numbers, sigma 1, sigma 2, all the way up to sigma 500. Right? I mean, let's assume the rank is 100. In this case, it is actually. And so if you just go ahead and do this, if you plot the singular values that you get, so somebody did this. There's a link to this on the web page, which also is a nice explanation of SVD. If you do this and you plot the singular values on a log scale, you get this. Okay, so log scale means this is log of the singular values, right? The singular values are some positive numbers, so I can take their log. You notice there are a few big ones and it goes down pretty fast. Right? And so, I mean, okay, you have to decide what you mean by big singular values, but there's a very natural approach to now compressing the image, going back to our little SVD. So the idea is throw away terms with small sigma I. Okay, so the observation, which is really true for real life images. So here's a sort of empirical observation. Empirical fact, most images have very few large singular values. We haven't defined large, but basically they're dominated by few. So the idea is, well, you can approximate this by you just throw away all but the top, let's say 50. Right? And now how many numbers, well, okay, so let's see how well that works, right? So this is now a rank 50 matrix, right? So let's call this A tilde. And now let's see how well, this is the idea. This is the key idea in image compression. And let's see how well it works. So this was the tiger. And this is what happens if you do this, right? So if you take the full rank tiger, as in you don't throw away any singular values. Okay, I would like to zoom in here, actually. How do you zoom in? Yeah. Okay, the resolution is kind of low, but the point is, if you know, after you throw away most of the singular values, you still basically get something that looks like the tiger, right? So this is a full rank tiger, rank 200 tiger, rank 100 tiger. And you know, you can still see that it's a tiger all the way down to a rank 10 tiger, actually. Rank 3 tiger is not looking so good anymore, but right? So the point is you can throw away information while still basically preserving what the image looks like. And so the punchline is that to store this, you need far fewer numbers, right? So you need 50 times, now you need to store two singular vectors per singular value. So you need 50 times 1,000 numbers, which is much smaller, right? This is just like 5 times 10 to the 4. So you reduce the size by an 1/8 without losing much information. And this really is somehow the basis for most image compression, you know, on the internet, for example. It's kind of surprising that some generic thing like singular value decomposition works. But anyway, this is one cool application of singular value decomposition, which is image compression.
Professor.
Mm-hmm.
So when you said that the most images have very few large singular values, but then you also said that they throw away the terms with the small singular values, do you mean that they have very few singular values and all of them are the larger ones?
No, so most images have a lot of non-zero singular values, like, you know, they have the maximum number, like 500. But what happens empirically for most images is that only like 10% of them are going to be big. All these other numbers are going to be much smaller. So what that means is that even if you just ignore those terms, right, it's not going to change the matrix too much. Because after all, A is the sum of all these terms. If you throw away the small ones, it's not going to change the actual matrix too much.
But doesn't that mean that they had very few large singular values to begin with?
Correct, correct. Oh, yeah. They had very few large singular values to begin with.
Okay.
What I meant to say is they still had many non-zero singular values, but very few of them were large, correct? So this is just sort of an empirical fact about real images, that if you take the SVD, they have very few large singular values.
Okay.
So in some sense, like images in nature are inherently close to being low rank, is one way to think about it. Okay, so I spent much more time on this than I thought. So I'm not going to be able to do much differential equations, but I will start doing it. But any questions about this application? Okay. So that's the end of linear algebra per se. And in the beginning of the course, I showed you this picture of this elephant that had all these different parts. And I hope you now see, the SVD is really shows that how all these different things that we did are actually very closely related to each other. What we're going to do now is we're going to start talking about differential equations. So second order ordinary homogeneous differential equations. And we now switch textbooks from Lay to this other book, Nagel, Saff, and Snyder, which is, I'm sorry to say, not well organized at all. And it's a total mess. So we are going to do problems from it, but by and large, we'll just follow my slides. So it's important to read the slides in this part of the course. We'll only do this for about the remaining 6 lectures. That's all that's left. So it'll be pretty self-contained. Okay, so what is, so let me tell you the motivation. So the motivation for studying this class of equations is something you may or may not have studied in physics, which is this model where you have a spring and you have a mass attached to the spring. Okay, so this is a spring mass system. And this is a block that has some mass m. And what you're going to do is you're going to maybe pull this block away from its equilibrium. So there's some like equilibrium position of the spring, right? When the spring is totally relaxed, there's some, some location, which I'm going to call the origin. And I'm going to be interested in the position of this block at time t, let's say of the center of the block, right? And so in physics, what happens is that if you have a block like this on a surface, there are 3 classical physical laws that tell you what happens. So let me just review what they are. So the first is that the net force acting on the block is equal to its mass times acceleration. That's Newton's law, Newton's second law, which is that acceleration is a second derivative of position. So this is my double prime t. That's one equation. And then there's something called Hooke's law, which says that there's a restoring force from the spring. And that's the spring has some spring constant K. And what this is saying is that the spring is trying to bring the block back to equilibrium. So it's going to exert a force that's proportional to the displacement, and it's going to exert it in the opposite direction. And then finally, there's this frictional force, which there's some model for friction in which the frictional force is just equal to, is proportional to the speed at which it's moving. So you get more friction the faster you move. And again, there's some constant, minus c. So it's trying to reverse the movement. So these are the laws of classical physics that govern the motion of this block. And, you know, in physics, what do we want to do? Well, you know, what's the physical question? So given that you know the position and velocity at time 0, what is the position and velocity at time t? Right? So these numbers are the position and velocity. This is okay, when I first saw this, I thought this was dumb. I thought this was some like super idealized thing that you learn in high school that like never comes up. But the more I learn about physics, the more I realize that, you know, this model actually, you know, souped up versions of it describe like very complicated physical phenomena, right? Like all of musical theory can be eventually described by versions of this equation, ultimately. This equation ultimately, you know, some version of it describes what happens in quantum mechanics. I mean, okay, it's a different version, but this is the basic building block of the wave equation, which describes, you know, a huge swath of what happens in physics. So let me, just to make it more visceral, let me show you a simulator in case you haven't seen this equation or are not familiar with it. It's kind of fun to play with. So, I mean, I like the simulator. So where is the simulator? Okay, I thought I had a simulator. Yeah. Okay, so this is some website with such a system, and you get to set these parameters. The mass damping is like the friction constant, and the stiffness is K. And then, you know, you can like pull this and watch it like, so you see what happens. It kind of oscillates. And then it eventually kind of dies out, right? Okay. And, you know, different things happen if you start with different. So if you start here and you move it really fast, then it has a different pattern. And, you know, you can plot these variables in different ways, right? So I believe in this case, okay, one of them is position and the other is velocity. And it's making some oscillating shape that's kind of slowly dying out. And we would like to be able to predict this, right? This is obviously an important engineering problem at the very least. So this is what we want to study. And, you know, the point is that this is some kind of equation, right? So, you know, the basic thing in physics is that the net force is 0, right? Because there are no other forces acting on this. So this function y is described by this equation. So my double prime of t plus cy single prime of t plus k y of t is 0. Right, I rearrange the terms, right? Because I have F net is equal to F spring plus F fric, right? So this is the motivation for studying this kind of equation. And this is what we're going to study. So let me now define the model. So the definition, a homogeneous second order ordinary differential equation is an equation of the form ay double prime plus by prime plus cy is equal to 0, where a is not 0. And these are real numbers. Okay, so and y is an unknown function. And what you're trying to do is find a function that fits this equation, right? So in this case, the coefficients are given by the mass, the damping, and the spring constant. That describes your physical setup. And yeah, if you want to predict what's going to happen, you have to find functions that fit this equation. That's a differential equation. Now, what does this have to do with linear algebra? So, okay, maybe before that, what question do we want to ask? We have two questions we want to ask about such a system. One is, what is the general solution? That means find all y of t satisfying the equation. Okay, just all functions that satisfy this. That's a well-formed question, right? And you know, it's a little different from the equations we're looking at because this is an equality of functions, right? The left and right-hand side are functions. That's the new twist that we have. Well, I mean, I made you do some of this on the midterm, but you know, we haven't really been doing it that much. So that's the first question. Given such an equation, which y's satisfy it? And the second question, which is called an initial value problem, is find a specific y of t satisfying the equation and some initial conditions. And this is called an initial value problem. So this is, you know, the obvious problem in physics, right? If I start the spring with some, you know, velocity and position, what's going to happen, right? Then I have these additional initial conditions. So this is the type of equation. These are the two types of questions that I want to ask about it. Okay. So for example, we have this running example, which we'll have, I guess we'll mostly be running in the next lecture. The example I guess I had written down, which we'll mostly be talking about in the next lecture, is, you know, you have an equation. I mean, I guess it doesn't matter. Yeah, I chose this one, y double prime minus 3y prime minus 4y is equal to 0. So by the way, so what do the different parts of this terminology mean? Homogeneous means the right-hand side is 0. Second order means only second derivatives. Ordinary means one variable. Okay, so for the rest of this lecture, I just want to talk about what does this have to do with linear algebra. So let's see that. So this is why there's one course called Differential Equations and Linear Algebra. So connection to linear algebra. The first connection is, so let's say you have an equation like this. First connection is, let's look at some vector spaces. Let F, or let's actually, yeah, let's use a little more maybe sophisticated notation. Let C infinity R be the vector space of infinitely differentiable functions from R to itself. This is a vector space, which we've seen before. Now, this vector space, the key point is, let T define the following linear transformation. So T of a function y is just exactly this, ay double prime plus by prime plus cy equals plus cy. That's a linear transformation.
Professor, what's the word next to infinitively?
Oh, differentiable. Yeah, let me just write it out. Okay. Now this, so this, you can check this is linear. It's not surprising by now, right? We've seen that, we've seen things like this are linear. It's a linear transformation between two infinite dimensional vector spaces. And so this equation is actually an equation that looks like this. And we have a name for that, right? That's the kernel. Is the kernel of this T, which is a subspace of C infinity R. So that's the first connection to linear algebra. That the solution set of this type of equation is a kernel of a linear transformation. So by the way, this equation always has one solution, right? Can anybody tell me what it is?
The trivial solution.
The trivial solution, 0. Yeah, that's a good old linear algebra fact. That's always there. But now, this is interesting because now we know that the set of solutions is going to be a vector space, right? So that's the first connection. The second connection, which is different, is something we've hinted at already in the homework and the exams. It's the following theorem. The linear transformation. So there's another linear transformation. S goes from the kernel of T to R2 by S of Y is just Y of 0, Y prime of 0. So this is something we've seen many times now. Is 1 to 1 and on to. Isomorphism. So this is called the existence and uniqueness theorem. So think about what this is saying. This is saying that if you want a solution to the differential equation, which matches a certain value at 0 and a certain derivative at 0, there exists exactly one solution, right? So 1 to 1 tells you something about uniqueness. And this tells you something about existence. So what this means is, this is equivalent to saying that this initial value problem, find a solution to this equation satisfying these conditions star. This is equivalent to saying that that always has a unique solution.
I had a question. Wouldn't that mean that because we're saying that, wouldn't S be an isomorphism then?
Yeah, it is an isomorphism.
Okay, so then isn't our like solution space going to be two-dimensional then?
Exactly, that's the punchline, right? So this theorem, whose proof is a bit beyond the course, but okay, maybe I'll say a little bit about it next time. The punchline is that therefore the dimension of the solution space is 2. That is a highly non-obvious fact, right? You write down this equation where the unknowns are functions. And this linear algebra fact that this thing is an isomorphism is telling you that the solution space of such an equation always has 2 dimensions. So that's good, right? Because in the beginning, like, what if the kernel was infinite dimensional? How could we possibly know what it was, right? How would we find it? So this gives us our bearings for this problem, right? That the solution set is now a two-dimensional subspace. And now next time I'll talk about how to find what that subspace is. So yeah, so that's it for the lecture.
Professor, is Gradescope going to address the 24-hour change on homework?
Yes, so I think there's already an extension on it, but I'm gonna boost it by one more day, yeah.
Thank you.
Any question?
Professor, can you explain like why Sy is an isomorphism?
Right, so we didn't prove that, right? So that is, I'll sketch the proof next time.
Okay, yeah.
We did not prove why it's an isomorphism. Actually proving it is a bit beyond the scope of the course because it requires some calculus that's a bit maybe beyond the course, but I'll sketch a proof. I mean, there's a very clear physical reason, right? So if you believe in classical mechanics, if I know the position and velocity of this box, right? And I let nature take its course, there's a unique solution, right? It's totally predictable, right? I mean, and that is exactly what this theorem is saying, that if you give me the position and velocity, there's exactly one trajectory that follows.
Oh, yeah.
So that's the physical reason why it's true, and not surprising that it's true, right? That if you give me initial position, initial velocity, you can predict the whole trajectory in these laws. Of course, the mathematical proof is, something else.
Professor?
Mm-hmm.
So in the reduced SVD, in the steps that you provided for the reduced SVD, I was wondering why you wrote that projection of rho A of X plus projection of null A of X.
Right. So here I used the unique decomposition theorem. So remember, rho of A and null of A are orthogonal complement subspaces, right? W and W perp.
Yeah.
And every vector has a unique decomposition as a sum of its projection onto W and projection onto W perp.
Oh, I see.
So X is necessarily equal to its projection onto the row space plus its projection onto the column space.
I see.
Does that make sense? Yep.
Yeah, it does.
Any other question?
Yeah, what does C stand for in the friction equation?
Yeah, so in the friction equation, C stands for, so maybe I should say, so this is, M is mass.
Mm-hmm.
K is the spring constant,
Mm-hmm.
sometimes called stiffness. And this is the damping constants, which is the friction constant.
Does that depend on the mass?
No, at least in this idealized model, it doesn't. So this is a simplified model of physics. And in this model, no, it doesn't. The C doesn't depend on the mass.
Is that the same as like the friction coefficient between like the block and the surface?
Correct. It's a friction coefficient. Yeah.
Okay.
Actually, I'm sorry. It does depend on the mass. You're right. It depends on the mass. But for now, we're just fixing the mass, right? We're assuming the mass is fixed. So given that mass, there's some fixed C. You're of course right. Yeah. If the mass is higher, there'll be more friction. Yeah.
Okay, great. Thank you.
Yeah.
Could you go back where you defined the second order differential equation?
This, yeah.
Yeah. What does RHS equals 0 mean?
The right-hand side equals 0.
Oh, okay.
Sorry, yeah.
Okay, thank you.
Professor, can you go back to the coefficient of the friction?
Yeah.
Like if C is the coefficient of friction, like why it has relationship with the velocity?
So that's just something from physics. I mean, I don't really remember, honestly. It's some law in physics. Does anybody remember why?
Well, obviously, the faster you're moving, the more friction you're encountering, right?
Yeah, that's intuitively clear. But I don't remember the derivation for why it's linear. Does somebody?
Isn't it something like once like you move and then the friction is like the same? Because it only relates to the normal force you got.
Well, there was static friction and kinetic friction.
Yeah.
You're probably right. I haven't done this particular friction for a long time. So I don't know. I don't know. I don't remember what the derivation is. But yeah, there's some static friction. There's some other friction. Somehow the friction is harder when is more when you're not moving, right? So in reality, it's not even linear, right? This is some approximation of that, which I believe is true. I don't know in what regime, but yeah. We're just going to import this from physics.
And like, Professor, can you go back to the interpretation of SVD?
Interpretation of SVD, which one? So there were two, right? There's a multiplicative interpretation of the full SVD and the additive interpretation of the reduced SVD.
Oh, just this one, the slide. Like why the matrix U1 V1 transpose will give you like a rank 1 matrix.
Right. So that will require, if you just do the multiplication, right? So like maybe you're not that, we're not very used to doing this. So U1 V1 transpose is like an M by 1 matrix times a 1 by N matrix, right? So if you just do the multiplication, you'll see that all of the columns of UI VI transpose are just all multiples of the same vector. So therefore its rank is 1. You can also just see it because, you know, if you multiply U1 UI VI transpose times X, you always get a multiple of UI. So the column space is just the span of UI. So the rank is 1.
Oh, okay. Yeah.
Yep.
Thank you, Professor.
Yep, thank you.
Professor, I'm your Math 49 student. I just wanted to clarify, I was here for DiffEq. I don't need to know the